All right. So last but not least, we're on to membrane transport. Now, membrane transport is the transport or movement of molecules. It can be mediated or non-mediated. Now, we've talked about secondary active transport and active transport as our primary things. There are also means in which a molecule can be moved across a membrane through simple diffusion. The rate of diffusion depends on the concentration gradient and the substance's solubility in the membrane's nonpolar core. We've got water, O2, and steroids. They readily diffuse across the membrane, so they don't really need anything to assist them. That doesn't mean that they exclusively move without a protein, but you know, they're going to do so without too much of an issue. There are things that can help speed that along, though. Now, um, there's mediated transport. Well, we've got two major categories depending on the thermodynamics of it. Our passive mediated transport or facilitated diffusion. These molecules are going to flow from high concentrations to low concentrations. There's active transport. A molecule is transported against its concentration gradient. Okay, so an unfavorable movement. This endergonic process must be coupled. So you got to combine it with something that's exergonic in order to make this movement thermodynamically favorable. Now, when we talk about movement across a membrane, the diffusion of a substance between two sides of a membrane thermodynamically represents a chemical equilibrium, or an equilibrium. A source to a destination. A being our molecule's concentration at the source versus a molecule's concentration in the destination. Now, we can kind of sum this up in a nice way by saying the difference in the concentration of a substance on two sides of a membrane generates a chemical potential difference. Delta G is equal to RT ln, and here's our concentration in the destination over concentration in the source. So this is our product over a reactant. The difference generates an electrical potential difference. That is depicted by this right here, our electrical potential difference. Z sub A, which is the charge of the ion, F, which is Faraday's constant, and delta psi, which is the electrical potential difference. Now, ultimately, we can combine these to make an electrochemical potential. Okay, so when we think about movement of a molecule across a membrane, we've got to think about the chemistry of it, the concentration of that substance in the destination or versus the source, as well as, well, is that substance charged? Are we moving a magnesium ion, a sodium ion, a glucose molecule? All those are going to have different charges. Now, that's where all this comes from. And we are going to put that in the context of, or put that in the terms of delta G. Is this a favorable move? Yes or no? That's ultimately our question that we'd like to answer. Now, here is basically our chemical reaction. A source, our reactants, to a destination, our products. Now, our electrochemical potential, delta G equals RT ln AD over AS plus ZAF delta psi. By default, delta psi is measured as the potential inside the cell, our destination, minus the potential outside of the cell, the source. Okay. A negative number indicates the inside of the cell is more negative than outside. So what that means is that if an ion moves from the outside to the inside, then the membrane potential is fine. So what that means is if you're given a question, or if you look at a situation where an ion, and you don't have to think about a cation or an ion is moving from the outside in, then whatever delta psi value has been provided does not change. So if you're moving out to in, I always think about this as out to in, NC, no change. Then you could say NC of delta psi. Sometimes when I write change of psi, I just get mixed up and I'm like, this is a fraternity or something. However, if an ion moves from the inside to the out, then the sign of the potential must change. So in to out, then we have delta delta psi. We change delta psi. Almost always, the cytosol is considered the inside of the cell. Additionally, if more than one ion is transported, calculate the free energy change for one ion, then multiply for additional ions. Now, this question is it favorable from a charge standpoint to transport a chloride ion into a cell with a delta psi of negative 60 millivolts? Okay, so there's our delta psi. Now let's think about this and apply what we just talked about. I'm going to go ahead and get a different colored pen so that I can keep track of this. And I'm going to say, all right, my point was if I'm going from the outside in, then I'm not going to change delta psi. Now, in addition to that, what I want to do is I want to look at this and not think about that part of the equation because I'm not given any information about my concentration. I'm just asked from a charge standpoint. So in terms of this, I've dropped the first part. My Z sub A, I'm going to put -1 because that is the charge of my ion. Faraday's constant, I'm going to put as 96. Delta psi, well, that is currently a negative value, but the question is, do I change it? Okay, so if an ion moves from the outside to the in, then do not change the delta psi. Is it favorable from a charge standpoint to transport chloride ions into a cell? What does that mean? Into. That means from the outside in to the inside. So in this case, I would not change it. So that means that delta, I'm just going to put it at delta 1, or sorry, negative 60. Now, in terms of doing this calculation, really, I could actually say -1 times 1 times -1. Why did I just substitute all those numbers for 1? Because it doesn't matter. Because I'm just trying to find out, is my delta G positive or negative? Because I'm not going to do this actual calculation. The magnitude of it doesn't matter. The question is, transporting an anion, is this favorable? And what I would do, well, this is negative. This is positive. This value, my delta psi, did not change. Therefore, my answer to this is no. It is not favorable. Now, what about transporting it out? Well, in that case, it's a different story. Then effectively, I've got delta G is equal to, well, let's see. The Z sub A does not change. That's -1. Faraday's constant does not change. That's 1. Delta psi, oh, that does change. That becomes positive. I'll say that's +1. In that case, yes, favorable. Okay. Now, would this have changed if rather than chloride, I had sodium ions as the answer? It would. Absolutely. It would absolutely change. Then my answers would be inverted. Okay. Now, to look at some of these actual calculations, I want to work through this and kind of do it in a deliberate way. Everything's all up there. So if you want to visualize and jump ahead, you can. But this question gives us our equation. And it says transporting sodium ions in or out of a cell when a delta psi is -60. The cytosolic sodium concentration is 12 millimolar. Okay, so that's our source or it's our destination. Okay, extracellular is 145 millimolar. That could be our source, that could be our destination. We don't actually have a question yet, but here is our question. What is the change in free energy associated with transporting sodium into the cell at body temperature of 37 degrees Celsius? Okay, I'm going to go back. I gotta remind myself of this. Out to in, no change. Out to in, no change. Okay, so in this case, let's see, I could basically solve this as two different things. And that's what I've got right here. Chemical potential. That is equal to RT. So R, you know what? I'm going to drop that. I'm going to go with my highlighter. R, there's my R value, times T, natural log of, okay, we're going into, so my destination is 12. 12 over my extracellular, which is my source, which is 145. So natural log of 12 over 145, that is negative 6.42. Now, this is a nice little calculation, a simplified version of the calculation if you're kind of doing some rounding and you're really comfortable with log rules. But if you're not, don't worry about it. You have a calculator that you can use. Okay, so from a chemical perspective, this is favorable. From the electrical potential difference, okay, so we first start with our Z sub A. We're moving a sodium ion, so that's going to be +1. Faraday's constant is 96.485 kilojoules per volt mole. Okay, so done. Delta psi is negative 0.06 volt. What? Oh, that's negative 60 millivolts converted to volts. So I need to reconcile the units there. So 0.06 volts. My value is negative 5.79 kilojoules per mole. Okay, so that's also favorable. So we've got a delta G of negative 12.21. All right. So how would this be different, or what would make this any different? Let's see. If it was chloride ions. If this was, if the only difference in this, if all the numbers were the same, but we were talking about moving an anion, that would change this, the Z sub alpha. A chloride ion would be favorable from a chem standpoint. Okay, check. Then Na plus. Ooh, that would be, sorry. What about from an electrical potential difference? Well, electrical, that would be unfavorable. So that would be a difference maker there. Now, we've got the same sort of thing, the same sort of problem, but rather than going into, we're going out of. When we're going out of the cell, what changes? Well, what changes then is from a chemical standpoint, does anything change? Yeah. When we're going out, then our cytosolic is our source, which is indicated right here, that 12. So I've got this chemical potential calculation right there. The extracellular concentration, that is my destination. My delta psi, oh, that remains this. No, it doesn't. It's now a positive value. Okay. So when we're going out of the cell as opposed to into the cell, that makes it unfavorable from both vantage points. Now, how would this differ if we're doing two sodium ions? Well, the only difference there is that we're going to do the same calculation. We're going to double it. We're going to multiply it all by 2. All right. So the important parts, some of the important parts about this is one, you got to keep straight. What are your numbers? What do they indicate? What do they show? In addition to that, try to think logically and deliberately through, is this moving inside or is it moving outside? Is this favorable from a chemical potential difference? Is this favorable from an electrical potential difference? These formulas are intimidating. They can be a little bit overwhelming. But if you break it down into individual pieces, then you can say, oh, well, this is favorable from a chemical perspective, but not an electrical potential difference.